Okay, welcome back, ladies and gentlemen. I'm going to introduce Guy Hudson, who's the Chief Executive Officer of Beneficial Environments. Personal items. His grandfather was a water diviner, and he ended up being a water diviner and a physicist. A business achievement he's proud of, helping to deliver water to 200,000 people in Western Zambia. He's going to be talking to us about electromagnetic life. And what he's going to do is he's going to explore the implications of electromagnetic life. And he's got 4 points. First one is, we're probably the shape we are, some of us beautifully formed, in proportion. We're probably the shape we are because of naturally occurring musical frequencies. Second point is that musical frequencies, whether EM or vibrational sound waves, can either support or hinder our health. So there could be a beneficial component to it. Third point is, what is the main problem that we need to tackle? And then his final point is, we need to avoid polarized low-end radio EM waves. Let's welcome Guy Hudson.
Okay, completely different theme. I would like you to cast your mind back, long time back in time, when in evolution, single cells had evolved. And nature was beginning to group them together and form structures. And so what natural structures were around to agglomerate the cells into structures? So the formation of waves in sand under the sea, the rustling of the trees, all producing sound waves. And the sound waves add up and taken away in space to form what are called diffraction patterns. And so, right, let's mark this. Oh, yes, come up. So here's a similar pattern. I'll speak in the microphone. Here's a similar kind of pattern, only this is taken like that dish we saw on the loudspeaker with differently lit. And so that we can see, you can produce absolutely wonderful biological type structures very simply with sound actuators. And there we're seeing that we've got electrical signals which are connected to basically a loudspeaker cone, which turns it into vibration, and then you get the beginnings of stuff that looks very biological. Here's another picture of biological. I'm sorry I haven't got the video here, but this looks like a centipede going along, and all it is a trough with water and a sound actuator on it, and it looks like a centipede. So I've missed. There we are. 250 years ago, there was a Czech scientist called Chladni, and he had a simple square table, which he then, the technology available then was a violin bow. And he got the same things that we saw in the video from that. And there's been a huge amount of work on that since then. But the interesting thing is that genetics gives us absolutely no clue as to our geometry. A huge amount is understood about the structure of the single cells, but the organization of those cells is not given any information by genetics. Before the dominance of genetics, there were a number of scientists working which showed showed time and again that it was electric fields that were causing this organization. So that there are a set of animals, rather primitive sea creatures, that if you put a voltage on them as they're growing, you can end up with like a worm with two heads or a worm with two tails, just by putting a simple DC voltage on them. And also they found that when higher animals have an injury, there is a voltage generated at the wound to encourage healing. So here we can see the hugely beneficial effects of electricity. Without this bioelectric stuff, we wouldn't heal, we wouldn't grow, we wouldn't constantly be repairing ourselves. I want to talk about the work of a orthopedic surgeon during the time of the Vietnam War. So in the 70s and 80s. He is called Robert Becker. So he worked in the Veterans Hospital in New York State, and he had to try and put American soldiers back together after they were being, had war injuries. And he had to try and set bones, and when he couldn't, he had to end up amputating limbs of people in the prime of their lives. And this really, really upset him, and he wanted earnestly to do something about it. So he began to look at the Northeast American newt called a salamander. And you can see the skeleton of a salamander. And this is, so that's the whole skeleton, and it's almost as complex as ours. And if you look at the front forelimb, you can see that there's a shoulder, there's a single bone, there's an elbow, there's two bones, there's a complex wrist, and there are 5 digits. Just the same as we are. So he thought, now, whatever he chopped off, I'm sorry for those people who don't like animal experiments, but whatever he chopped off, a salamander, famously lizards' tails chopped off and they regrow time and time again, but the same with the front leg, and almost the same with anything else, other part of he experimented with. And so it was of great news to him that this would faithfully grow again. So he started doing the obvious thing, which was to look at this limb regrowing. And what you can see is the same front forelimb after it's been chopped, and how it's regrowing. So first of all, the skin starts to grow round, but then a very interesting thing happens, particularly to the nerves. The nerves degenerate and regrow. And so this is a blow-up of that, where you can see the nerves have grown into the skin. And inside that cluster of nerves, like the roots of a tree, is a cell factory, which is making stem cells. So that's our genetics hard at work, reproducing those cells. But those cells migrate into position and to where the nerves are. And so it was his supposition that there's a process called differentiation, and we can see here that you start off with a stem cell, then it goes into 3 different kinds of cells, and then it goes into 9 different kinds of cells. So the different cells were skin, nerve, muscle, bone, cartilage, fiber, blood, gut, and liver. And so how can that be happening? Why do these nerves grow into a kind of framework which then at the point where the cells are migrating there, and they become all differentiated into these 9 different kinds of cells to regrow the limb? Well, as a physicist, it's pretty obvious. Nerves go on electrical signals, and so they must be creating some kind of 3D pattern which those cells respond to when they get into the right position to regrow the limb. So one other interesting thing, Becker was twice nominated for the Nobel Prize, and what he was nominated for was a bone regeneration little electrical gizmo. So it sent out a signal, so if you've got a large bone that's broken and it's not mending, you'd connect the wires to either end of the bone, a signal would go there based on what he found here, and it would encourage the bone to grow, knit back together. So it's a huge step forward, of course, nowhere near as complicated as what he'd witnessed in the salamander. What he also found is he tried to get it to work on a slightly higher animal, the frog, and it wouldn't work until he stripped this is a horrible thing to do, but anyway, he stripped the nerve out of the back leg and put it in the front leg, and it had enough power in the nerves then to cause the regeneration, and the leg regrew. So that gave him the idea to do the electrical machine. But also, the higher the animal, so each kind of animal has got similar percentage weight of nerve tissue in it, about 7%. but the higher the animal, the more it gets concentrated in the head for a bigger brain. And so in terms of evolution, we've benefited from having a bigger brain, but we've lost the ability to regrow complete limbs with that. However, for pre-adolescent children, if they have a damage, which is quite common, where trapped in a car door, it chops the top of a digit off, then providing it's left in a right old mess, it will actually regrow, providing it's above that first the end knuckle. So lots of reasons to be cheerful in terms of getting this going, but he never achieved much more than that. But in the development of his bone mending machine, the critical thing was that he had a very talented lab assistant, and unbeknown to, they gave up trying to get it to work because they couldn't get it to stimulate the regrowth. And quietly, on his own, he kept dropping the voltage of supply. And only when the voltage went to tiny amounts, so the currents involved were tens of microvolts, which in those days, in terms of technology, was the absolute sort of smallest they could get down to, it began to work. So what that means is that these signals, in order to influence what a stem cell does, have got to be absolutely tiny. And that, of course, gives us, if our bodies respond like that, that gives us a big safety net. So as soon as there's a thunderstorm, we don't all just dissolve and become soup on the floor. We actually continue going because it's above the threshold of influence. So if we can go forward 20 years or so, and over to Cambridge University, there's a mathematician working there called John Evans, and he was an applied mathematician, and his life's work was to create a suite of software, actually based on the same mathematics I used to use when doing crash simulations in the car industry. You block everything up so you can make complex structures in space, the virtual space inside the computer, and you can assign particular material properties to that, so it behaves in a particular way. And with his software, it was all about modeling electromagnetics. And so you're able to put aerials or transmitters or receivers into this software, and you can try different aerial configurations or different speaker cones if you're designing loudspeakers or whatever. With very good software, worked very well. But his hobby was bioelectromagnetics. He was interested in biological shapes. And so he started looking at the human form, and this is a 3-week-old human embryo when it's just a few millimeters long. The first nerve tissue to grow are what's called somites, and they're little pencil-like structures that eventually become our ganglia. So the key parts of that's it. So each of these ganglia, they are the lumps of nerve which grow in between and in front of each vertebrum on our spinal column, actually innervate or do the nerve job for these different zones in the body. And we can see that there. So what he saw was that he looked at the ratios of the sizes of the different vertebrae and saw there was a 1.06 ratio between a lot of them, and the musical amongst you know that that's the difference in frequency between the notes on a piano. And so he intuited that actually there would be the alpha waves in the brain. Electroencephalograms show that at heart level it's about 500, which is very close to middle C. So he did a musical sequence. He thought what he'd do is build a mathematical model based on that geometry with 44 double little aerials. So he intuited, those look like aerials to him. And he thought, I bet, now there's 1.06, bet it's musical, and let's see what we get. So he put it into space. He made a sort of virtual tank of amniotic fluid, put those little aerials into it, and he put different musical note. So musical so far, la, ti, do, right the way down the spine. And this is what he got. He got a baby. It's very grainy, and it's very, not very attractive, but given the resolution of the model in terms of the simplicity of the mathematics, and if you cut, this is in 3D, and if you cut a section through it, it's circular. So you can see that there's a ball, which looks very like a head. There are two eye sockets, there's a nose, there's a mouth. There's a narrowing where our necks are. There looks something a bit like a thorax. And there's beginning of 4 limbs. Now, so there, and there. So, and by tweaking the model a bit, by putting some extra things, he introduced asymmetry internally in the beginning of internal stuff. So I don't think you can look at that without saying, wow, that looks like a baby, and that's the beginning of our structure from such a simple model that needs a lot of tweaking. Now, that's in 3D, so what we're seeing is, while you're looking at the graphics of that, it's dynamic. So it's almost like looking at ripples of water when someone drops a stone in the pond. You're seeing that all of that is patterns of ripples, and that's just a freeze frame on it. Now, if you add to that, there are many structures in our body that convert electrical into vibration. And so electrical into vibration is like a loudspeaker, and there are also devices like microphones within our body where if there's sound pressure on it, it produces electrical waves. So actually, this model we're talking about is a bit oversimplified. That's only electrical. It's also acoustic. So this is, for me, the way that we grow and why we grow the way we are. And it's a really fundamental finding. Now, So really, the question goes, I mean, we as electrosensitive, when we go and see our doctor or talk generally, it's all about convincing people that electromagnetic waves do have an effect on us. Once you see this kind of thing going on, and this is only one of many, many electromagnetic effects on bodily processes, the question is not, is this an effect, but why aren't we affected more? Why has it taken this long, this degree of electrosmog, before we get so badly affected? And so there must be things that are protecting us, and I will be talking about that later. Thank you very much.
Thank you.